In this video, I'm going to show you how to use the program for the probability of exceptions for a binary predictor. I'm going to come down here to where the button is for it, and I click on that. When I do, a set of instructions appears in the description box for how to use it, and then we'll be inputting information into the input values box here. But first, let me give you some context. The program calculates the probability of exceptions to the rule based on a regression coefficient in a multi-predictor regression equation that takes into account covariates when evaluating it. It applies to the case of a binary predictor. For conceptual details, see my book. When we observe a mean difference between groups, we often form a rule based on that mean difference. For example, the mean height of males is larger than the mean height for females, so we form the rule males are taller than females, or males tend to be taller than females. But there are exceptions to this rule. Just how often will we encounter a situation where a female is taller than a male? How many exceptions to the rule are there? One way of answering this question is that if I randomly select a male from the population and a female from the population, and I do this repeatedly, on how many of these draws will the female be taller than the male? What proportion of times do I find an exception to the rule? This proportion is called the probability of exceptions to the rule. It is a statistic that reports the proportion of times that I observed exceptions to the rule, given I repeatedly randomly sample pairs of individuals from each group and compare the two individuals selected. There is a non-parametric version of the statistic and a parametric version that assumes the continuous measure is normally distributed in each group. One reason I like the parametric version is because I can control for covariates using it. I cannot do so for the non-parametric version. Also, simulation studies suggest that the parametric version works reasonably well, even when the distributions are decidedly non-normal. For details, see my book. As examples, suppose I have a binary mediator that is parental use of guilt when disciplining their child, and the outcome is child depression. I might find that the mean child depression is higher in parents who use guilt than parents who do not. This leads me to form the rule, parents who use guilt as a discipline strategy tend to have children who are more depressed as compared to the children of parents who do not use guilt. But how many exceptions to this rule are there? Or, suppose I have a program designed to increase adherence to one's medications, and I find that adherence is higher in the treatment condition than in the control condition. I form the rule that people who participate in the program tend to have better adherence than people who do not participate in the program. But how many exceptions are there to this rule? In this program, you can answer such questions using covariates or not using covariates. You regress the outcome onto a dummy variable scored 0 and 1, representing the binary predictor of interest, and then you enter the information the program requires. If you conduct a regression analysis with no other predictors other than the target predictor, then there are no covariates. If you conduct a regression analysis with other predictors in addition to the target predictor, then these other predictors are statistically controlled. For example, for the guilt example, I might want to control for biological sex and SES as reflected by annual income when conducting the analysis. In theory, I randomly select two parents from the population who both are, for example, male and who both earn $40,000 a year, and I do so repeatedly. In what proportion of the cases will the parent who uses guilt have a child who is lower in depression than a parent who does not use guilt? This reflects the case where I'm calculating the proportion of exceptions to the rule, holding constant biological sex of the parent and the annual income of the parent. See my book for details. Let's do the program using the guilt example. Suppose the child depression measure ranges from 0 to 10, with higher scores indicating greater depression. I regress the depression score onto a dummy variable, scored 1 equals the parent uses guilt as a discipline strategy, and 0 equals the parent does not use guilt as a discipline strategy. I include parent biological sex and annual income as covariates in the regression analysis. Suppose that the regression coefficient for the use of guilt variable is 4.0, so I indicate that here. That the squared multiple correlation is 0.15, and that the standard deviation of depression across all participants in the study is 3.5. I click Register Input to generate the R syntax. That's generated here. I copy that to the clipboard. I start R. Here I'm going to hit Control V to paste the syntax, and when I paste it, it'll automatically execute. The output appears in blue and the syntax appears in red. In this case, the probability of exception to the rule is 0.19. If I randomly select pairs of parents from the population who are equated on biological sex and annual income, the proportion of times a parent who uses guilt will have a child who is lower in depression than a parent who does not use guilt is 0.19 or 19%. You can apply the probability of exceptions concept to continuous predictors as well. See the companion program for continuous predictors to do so. Okay, that's it. Thanks a lot.